that I left the one last topic because of the time in the last lecture. So I will just do that quickly and just kind of go to second lecture topic. So last lecture, I just tried to describe the transport phenomena in the three different regimes. One is a diffusible regime, and which is rather that's straightforward. I think there's that kind of Boltzmann equation works well. And we discuss about the various transport coefficients and how they are related to each other. And more like it kind of in the simple manner. And of course, once you just throw in the interactions and correlations, and of course, those kind of the simple relations such as Wiedemann-Franz law and Mott formula and those kind of things were violated. And then second part that we discussed about the kind of quantum limit, especially in the ballistic, and then we start kind of the quantum treatment. And quite interestingly, I mean, basically many things start quantize, electrical and the thermal conductance start quantize, even the thermal power in quantum limit, for example, that the entropic relations that associate with this, the edge-related transport, often the thermal power peak has some of the quantization. Not straightforward. And the last regime that I didn't discuss about is so-called the hydrodynamic regime. I think this is something quite recent. It start kind of acquire the attraction. So we'll start with the Navier-Stokes. If I just look at the Navier-Stokes, in some simplified version, I can write down a V for that. This is the one side, and the other side I have the pressure gradient divided by rho mass, and then nu Laplacian of V plus now E of M and delta phi. So that's more like the EM drive. In this side is clear. This is nothing but just kind of total derivative of the velocity. And if you just kind of have the fluid that you have the kind of co-moving frame versus explicit derivative, in some sense, often that this is kind of convection terms that kind of provide. Most of the cases that are pressure, especially the degenerate electron gas, unless you have the huge density difference set up in your system, which is a little bit harder and often, the pressure terms, it's not necessarily important. Or potentially that typical case we ignore this. And this second term is the rather important term. It's actually involving in the viscosity or the moment at the viscous distribution of the momentum, and often that this is a kind of the viscosity. The more precisely is the kinetic viscosity, where that the unit is in terms of the diffusion coefficient, by the way. So meter squared volts per second is the units of this kinetic viscosity. It usually comes from the electron-electron interactions in our cases. So this will just kind of give us of the hydrodynamic effect, the CV hydrodynamic effect, and this becomes kind of a driving system. Now, in these cases, we just didn't throw anything about the disorder or the momentum relaxations, the ohmic terms in some sense. So in typical solid, of course, we cannot get rid of this impurity. So therefore, we have to just throw into this how that elastic scattering comes in. So we have to introduce this scattering terms, usually comes as gamma, or inverse of the momentum relaxation time, which actually in principle that if I'm Ohm's law can be obtained by measuring sigma, DC sigma, and multiply all these things. This gamma equations can be rewritten in terms of, okay, so we will have this convection terms as usual. But then the other side, now I just draw a pressure term. of the V. And now I have to just explicitly introduce the momentum relaxation. As usual, just Langevin terms like the gamma V. And then we have just the all other dry forms. Let's put down the explicitly. You can even, hydrodynamics, you can even just include the Lorentz force in there. That's basically governing equations that we have that describe the electrons in so-called hydrodynamic regimes in principle. So that is the, yeah. Yeah, that is rho is basically density, right? The electron density. So yeah, just kind of throw it away. Anyway, so yeah, for now. Because that's related with the kind of pressure of the electronic system. So if I just kind of think let's say that if I have that the degenerate system, this is usually kind of Pauli pressure, if you want, and that depends on density in there. Now, unless the density gradient is setting the system, if I just consider that electron gas that I'm dealing with, more like this close, incompressible base part is not too important. That's what I was told. I have never seen that actually use this one, except to discuss about some plasma type of the physics. Pressure becomes quite important, but people usually just kind of using this one. Of course, this equation is rather complicated to solve. I know that Navier-Stokes itself is difficult, and of course now we throw in the the ohmic term here, it becomes probably even harder. So that can be solvable. But nevertheless, there are kind of few important parameters we can consider to classify the transport regime, and that's kind of where that I want to kind of start with. Basically, viscosity coming from the electron-electron interaction. If you just go through the Fermi-Leakey theory, and viscosity can be more like the written in terms of v squared divided by 2, and electron-electron scattering time gets in. That's a part. I think Andy is around, and probably he can correct that. We have about getting the momentum relaxation. But let me just kind of ignore that for now. Now with this, basically, typically what you can see that is, if I just ignore this part, this becomes kind of more like the Ohm's type of the equations. Eventually, I can get down to the more like the ohmic discussions, right? If I ignore this one, this becomes a Navier-Stokes, right? So kind of complete hydrodynamic. Can roughly see that there is a comparisons that whether system behavior like more like the hydrodynamic versus whether system behavior more like the ohmic type of behavior. And of course, the relation we want to kind of compare with is this momentum relaxation, which is related with this gamma, and then nu, which is like this. So which one is bigger than, so where that if this time is bigger than this one, and then it's going to more like the ohmic behavior or diffusive type of things. And this time becomes shorter. This is hydrodynamic. That's kind of one thing we can just do that. The important, the length scale that we have to just to do that is what is the effect of the boundary into the system. I think the one essential part of the hydrodynamic equations or hydrodynamic transport is, unlike the ohmic relation, where everything's in principle, that write down the local relation, that local, connection is kind of broken, then I have to consider the system as a whole, especially all the boundary conditions and those kind of things becomes important when we just describe this, the fluid dynamics. Distance toward the boundary, or the compare with the size of sample, how much of the boundary effect becomes important, is it need to be considered. And especially in this hydrodynamic, the Navier-Stokes Ohm equations, there is a kind of one important length scale that we have to consider, that is so-called length scale. And that's defined. Note that nu is basically same unit as a diffusion constant. In other words, the one way that I can just know nu here is what is the electron momentum diffusion coefficient considering the electron-electron scattering. And naturally, the common with the length scale is that time OM. And this Gauge length scale is something that give you that length scale of the boundary condition becomes kind of important considering both of the hydrodynamic and the ohmic condition, right? So often that when LG, the Gauge length with the size of the system, characteristic size of the system, than this, this is where the cause effect is cause effect becomes appreciable. And the mean that I will show you the few examples of the experiments that what exactly does it mean. So basically comparison of the size with the Gauge length becomes kind of important. Right. Yes. No, I think electron-electron scattering length, if I just kind of look at there. First of all, the electron-electron scattering length scale that if I just write down, I think I would say, what is it? That I can just kind of, for example, right? And the Gauge length scale is kind of, see that it has contains electron-electron interaction or tau E, but also there is kind of the related momentum relaxation. Yeah. Let's see. If I kind of the diffusion constant, okay, so what you're saying is that you want kind of look at the momentum diffusion here, and that's, you're right, I think. On with the diffusion length scale and define in that way. It is in that way. But what is a physical, why you want to use a diffusion there? So if I just kind of use a diffusion constant, there is basically seeing that the momentum diffusion, right, of by the impurity. So if I just kind of use that, how to interpret that diffusion length scale is a part is exactly kind of same way that define the Gauge length scale. In a sense that you can see that when you just kind of move away from the boundary, right? My interpretation is that at a certain length scale that the viscosity effect becomes kind of important, and beyond that length scale, that beyond the Gauge length scale, that effect coming from the viscosity related with boundary effect becomes kind of weaker. I think that's my way to interpret it. But anyway, so let's see that slide. Here that I'm showing you that kind of various different length scale, that comparison and what is a transport regime that we can just put up there. Yes. Say again. 1 over gamma. Yeah. Right. So there are three length scale that get involved. One is length scale or the time scale. Let's say in terms of length scale, that same as time scale if I convert with the VF. And this is basically the diffusion length, the momentum relaxation length scale, and this is electron-electron length scale, or the conversion rate. And I'm just kind of normalize everything with this the size of the system or the characteristic length scale of the system. And clearly you can see that, for example, that this line is simply comparing that whether whether electron-electron scattering time versus the momentum relaxation time comparison, which one is important. So in the kind of traditional way that this is probably a line that roughly divided up where that you get more of the hydrodynamic side of the transport or the non-hydrodynamic side or ohmic type of the transport the part. And of course, you have to compare with the length scale, that mean pre-path of the system size. And if the mean pre-path either is electron-electron or the electron, the inelastic scattering is smaller than system size, or the length scale becomes larger than system size, the transport becomes ballistic. So at some point, you have the ballistic transport is defined in this region, right? And then that another length scale I just kind of put down is that this is basically kind of Gauge length scale, right? So this is kind of below here that compare with the size of the system. Above here, that basically size of system becomes kind of larger than Gauge length scale. And below here, that size of the system becomes smaller than Gauge length scale. So in some sense, I get the hydrodynamic transport kind of around here. But truly, that the manifest, a strong manifest of the hydrodynamic effect, such as kind of wall force and all this, the fluidic type of effect is somewhere in this kind of the corner, above beyond the ballistic, and but then yet that the viscosity kind of plays kind of quite important role. Yes.
Is there a difference between these two type of ballistic?
Yeah, that's a good question. The most of the ballistic I just discussed yesterday is more like this side, right? That I just ignore that through the electron-electron interactions. Now, of course, here that is a kind of ballistic where I have now it is. Yeah, so that is probably deeper. I have no good answers about that. In principle, you can just describe hydrodynamic type of the discussions with the I'm not discussion by myself. In fact, I just don't give you that my group's experimental result that we are working on. We are working on somewhere in these regions, and then we are suffering, especially thermal transport description. There is no proper description of the ballistic with this hydrodynamic description, and that the issues. Once you just get over onto this region, where then you can just have all the local equations you can write down. Right, but in this region, basically, it becomes kind of harder. I know that Leonid Leftov is coming next week, and he's probably the right person that discuss about that regions. And then, indeed, sometimes that hydrodynamic versus kind of the ballistic, including the electron-electron interaction, is a bit tricky. That's what I understand. Yeah.
Related to the Reynolds number?
Not really. Right. Yeah. That's kind of different consideration. Usually, Reynolds numbers here is not too important because the electron mass is so small compared with the real liquid system. So in typical velocity that you just kind of expect, kind of put in all these things, the Reynolds numbers is never been kind of really big issues for, as far as I know, the electron hydrodynamics. And of course, getting the high Reynolds number becomes quite exciting, right? It's a little bit difficult kind of achieve in most of the electronic system, as far as I know. Right, yes?
Have we ignored all inelastic scattering processes here?
So in a sense, electron-electron interaction is an inelastic scattering for single electron point of view. Now, I just throw out all this electron part or other degree of freedom. If you start to throw in there, becomes again complicated matters, right? Because you have to kind of bring another system and kind of couple the system. So that's also a harder problem, I know. One thing kind of close, which actually also kind of exciting, graphene getting into the charge neutrality, then you can start to see the hole comes in, right? So then you have not only electron-electron interaction, there's the electron-hole interaction, hole interactions. Already that give you the flavor that if I start to include more of the so-called inelastic channels, how the system becomes kind of quite the complicated problem. Brief discussions with a couple of experiments that out there that I mean, there are quite many, and this is one of the was claimed to show that hydrodynamic effect in the solid state. It's about 10 years ago, and then this is Andy Mackenzie's work that onto this palladium cobalt oxide. Somehow this oxide, it turns out, comes around extremely clean, and that when they measure the mobility, despite this is oxide, the mobility in the system is very high. In other words, the mean free path is kind of quite long, and long mean free path means basically we get into the quickly those kind of this hydrodynamic condition meets. What they did is basically they make the samples with the different kind of constrictions, and then and try to measure the resistance across the different sides of the constrictions. And experimental observation is basically when they see that how that Ohm's law worked it out. Ohm's law worked it out basically length versus width and those kind of things. Basically that the resistance is not scaled with this width of the device. Let's put it this way. So that's kind of what they are seeing, observing, right? And kind of this deviation is kind of something that, oh, well, you know, the Ohm's law start to break down. That's kind of some good indication. This type of the experiment was repeated in many other samples, for example, graphene and things. And then what is being observed is, say, when you have the constriction is building up, and especially this constriction, that the characteristic length of the device is comparable to the gauge length, right? And then you start to see that Ohm's law start kind of really start to deviate. In other words, that resistance you can define, well, in other words, the resistivity start kind of not defined well in terms of the Ohm's law. I think that's basically kind of observation. A little bit more, the observation I would say of this hydrodynamic effect is, again, this is a graphene sample done by Andre Geim's group in Manchester. What they see that is in graphene, again, you can make the graphene extremely clean. That mean free path becomes kind of quite long. And then you go to the higher temperature. That remember that I need kind of really small tau e. In other words, that electron-electron scattering becomes kind of readily happen, and electron-electron scattering, the rate proportional to the temperature square. So going to the higher temperature is a way that I can get into hydrodynamic. Indeed, high enough temperature, something like the 200 Kelvin, what they see that is when they measure the transport across it, some of the electrode they are seeing that supposedly read this positive resistance, positive the voltages according to the ohmic flow, they start getting negative resistance in some part. Kind of the carefully mapping that idea in there, they just kind of speculated, and indeed those kind of negative vicinity resistance appearing in the system can be explained that some of the current path is kind of coming back, so-called this Wolf type of defect, and that's kind of the experimental, the interpretation of the data. And important part is those kind of Wolf formation and those length scale is again governed by gauge length scale, such that this only appears when you make that the sample mesoscopic enough, such the gauge length scale here that is about that half of the micron is within this the device scheme, the measurement, right? More direct than this measurement is coming from the real space kind of scanning imaging, and there are a few groups actually. I'll just pick up the one of the result here that this is coming from Harvard. The various collaboration, including myself, Amir Yacobi, and Ron Wordsworth. Here's a graphene device again, but full idea is using the scanning the NV microscopy that one can detect this the local magnetic field, and measuring this magnetic field in the system can give you that the mapping out the what is the current path in the system. Therefore, you can just map out what is the current distribution into your channel by just kind of looking at this MB signal. In the end of the day, what has been seen that is indeed the current profile, if this is kind of channel length scale, shows a on the front. Basically, the current is flowing more into the center, and then there's a kind of less amount current is flowing there. In other words, if I just convert that in terms of the velocity of the electron flow, there's a higher velocity there and the lower velocity in another way, right? So there's basically the, if the current is kind of flowing there, electron current is flowing there, there's kind of nice profile of this velocity profile is coming there. And that's kind of exactly kind of what we expect to see that when you just flow through some pipeline, and if you just the viscosity effect coming coming from the pipe wall. Basically, those kind of nice profile, they often called the pose flow into the fluid dynamics, is one of this really direct indication that indeed electron flow here is described by the hydrodynamics. So as you see here that once you get into the cleaning of sample and going up the higher temperature such that viscosity becomes important, and transport can pick up those kind of hydrodynamic behavior, which means that now that can just kind of, you cannot describe this as a local, the connections or local properties, but you have to consider the system as a whole, and especially size of the system becomes comparable to the this length scale. You can start to see that this type of effect really appears as maximized. I'm skipping around that most of the other discussion, especially what is the effect of the thermal transport in this system, and obviously the thermal transport, thermoelectric transport altogether that kind of strongly deviated what we expect to see that the other transport regime, in particular because the hydrodynamic transport is a really inherently non-local behavior, non-local the phenomena. Therefore, that you start to see that kind of rather different the behavior. Yes.
Real experience, some are not really whole bar square shape. So any deviation in the boundary would affect the hydrodynamic.
In principle, yes, yeah. But by the way, this type of the samples, it was created by just etching it, right? So it is kind of indeed kind of coming in that way. I actually find that the nice images here, right? The sample, right? I believe that later version of the group, they indeed make some of this type of the shapes there and how current that flows and traps, right? Like the kind of the water flowing through this type of the device. You can just do that. Some of the fancy what I've seen is so-called make this Tesla valve, make this some system the structures the geometry in that way. So flow is flowing the one direction, but flow is easily flow the other direction. So make the kind of non-reciprocal the structures. I think there are kind of many fancy versions. One can just do that. Yeah. Yeah. So I think that escape around is in that way. In the Cavino geometry, you can just do that. And also exciting thing there is applying the magnetic field and start kind of current start kind of bending around, right? But then with the hydro, especially Gauge length is comparable to the size of the radius of the curvature of the Cavino device, then certainly the hydrodynamic effect, it becomes kind of important. Appears both in the conductance, electrical conductance measurement, as well as the thermal transport measurement. Yes. Okay. The final comments on there is, of course, hydrodynamic transport becomes also kind of exciting that once you get into really strongly correlated system, right? And even kind of correlate such that you have to throw away that all this quasi-particle behavior. In some sense, hydrodynamic the transport only relied on several of the conserved quantities, right? So those kind of system can be also, in principle, discussed in terms of the hydrodynamic type of the transport behavior. So that's kind of something that you can also ask Subir Sachdev, who is coming the next week, who also working on quite of this type of the behavior. Okay, so that much is that the first stage the topic. Then now let me move on to the second topics. So I already spent about 30 minutes, so I have to a little bit go through a little bit with the speed for the lecture 2. So in the lecture 2 that I'm going to discuss about not a DC transport, but AC transport. AC alternating current means that kind of various meaning that in fact anything time dependent type of measurement, you can say the AC. If you just drive really fast, it can be optical ranges, which actually already Peter covered nicely, right? Or you can just go down through then probably terahertz. That again, that up to there is optical techniques, right? Now you can just go even below the frequencies, and now you can microwave range. It's something like the gigahertz, tens of gigahertz ranges, 100 gigahertz ranges, or maybe even megahertz ranges. So radio frequencies. So that's basically the range of the frequency I'm going to discuss. So there's something like the megahertz, tens of megahertz, 100 megahertz through the kind of gigahertz ranges. And frequency ranges often in terms of the energy scale, h bar omega is much smaller than any of the gap we have, even including the superconducting gap. Therefore, you may say that, well, that I don't have the real transitions happening with this frequency. What's the deal about it, right? I'm going to actually claim that, in fact, this AC type of the measurement will immediately give you the really rich information. And then typically, experimentally, already it's richer because the DC transport will give one number, right? I'm just sending the current, measure the voltage, one number, right? I just kind of turn this into the AC, at least I start to get the two numbers. What is the response of the amplitude? And because it's AC, there's a kind of also phase relation, right? So amplitude and phase is already two more, the kind of double the information that I can get at the DC. So experimentally, it's already much more things that you can think about. So that's kind of the part. I want to actually also connect this topic with a little bit more the current topics and that people are kind of talking about. And to introduce that, because I don't know that topic well, let me see that something that I know. And starting with the challenge video. So I just copied this one from the Charles Kitter's Introduction to the Solid State Physics book. I think we have everybody here is a graduate students showing this one. You got insulted. I don't want to kind of read back to the Kitter's introduction of the solid state physics. However, actually, Kitter marked that this is one of the problem sets, and this problem is somewhat difficult. Indeed, I think this is a slightly more challenging than a typical undergraduate version, but whole idea that is basically K dot P theory, which is well known. So if you just apply the K dot P theory for the any block electrons, basically you can show that as this problem setting there, you can see that the energies, or dispersion of the block electron, if I know the K equal to 0, and can be written in this kind of form, and that basically how that it work it out and show it. Basically, start with this the second. As you see, the second order perturbation theory that applied to the block Hamilton, you can just easily show this one. Not easily, but you can show this one, right? Why that is kind of interesting, because if you just go back and ask a standard way, how we can just drive the effective mass of the system, right? And this is a way that you can always kind of bump to it. If I just look at this one, that dispersion relation is this K squares in this way, but you can quickly see that this, if I just kind of the factored out K here, they're out there, altogether this one becomes kind of the defined dispersions. So you can quickly see the effective mass, in fact, can be expressed in this form nicely by just kind of showing this one. Next one is almost follow, right? So we may ask the following things. So we naturally know, yeah, you know that if you calculate the band structures, I know that dispersion will give you so-called effective mass. Second derivative of the band dispersion give you the effective mass. And typical solid effective mass, unless you are dealing with heavy fermion, effective mass is usually, it's about electron mass or smaller, especially if you go to semiconductor, effective mass can be quite small, right? Gallium arsenide is only 6% of the bare electron mass, right? You may ask that, why effective mass is so different from bare electron mass? Oh. Right, yeah. Well, answer is here, right? Effective mass is here, m star, is differ from m, differ from 1 by this, right? And that's kind of how the effective mass becomes different, smaller or larger, right? But what is this term tells you? Where these things comes from? Well, this is second order perturbation, but basically connecting between the band that you are working on with the band that we are at the band away from down and up, right? And this is basically second order perturbation. I can see that it's kind of virtual transitions, right? That I consider, and that's what massively renormalize your bare mass, right? Even the kit does something a little bit deeper. So way that I can say that my effective mass of this band is different because in some sense, all other band I have to consider. Right. So that's basically kind of one conclusion I can quickly make out of this. Is something that my view that when I just first heard about these stories about in the solid, is it exactly reminds me the K dot P theorem that I learned when I was in graduate school, right? So there's various way that you can express the quantum geometry. I'm not a theorist, and probably you guys know much better than me, and maybe we can have even just better theorists can explain this one. But in the end of the day, whole idea is that each of the band has this quantum geometry where the real part is quantum metric and then the imaginary part is Berry curvatures. But even for the Berry curvature, not to mention the quantum metric, that relation that whether all these virtual transitions between the other band, unoccupied bands, basically plays an important role to just kind of explain that the property of the band that we are considering, especially if you just consider something like this dipole transition or dipole fluctuation and those kind of things, or effective mass, for example, that's included, becomes kind of quite important. One of the major constituents here. And more important part is those kind of transitions we have to consider in other band is more like the virtual transitions we have to consider. Right, so that's the connection. Why I'm saying this now? Because that's we may ask that what is a physical observable that relate with those kind of quantum metric, right? There are theories that kind of explain a few things that expect that a few things can just observe experimentally. For example, that there's one really nice theory by the Thoma and colleague that explain that if you have this the superconductors or superfluid, basically if you just look at the quantum geometry and then the Chern numbers, there's kind of some bound condition is kind of expected to happen. If it is a really topological superconductor, the quantum metric has a lower bound and cannot be smaller than that, and then this quantum metric can be quickly turn into the superfluid stiffness. So according to this paper, basically, if it is topological superconductor, no matter what, superfluid stiffness has kind of lower bound in there, right? Some of the another kind of theory that it was done by the Raquel Quiros, that in this case it is not a superconductor, but this is insulator, and that explain the theoretical expectation here is if you just look at the electric response of the insulator, and this dielectric response is related with, again, the quantum geometric, more precisely quantum metric into the system. And those kind of thing is something that principal one experimentally and see one explain this into this kind of quantum geometric effect. And that's kind of something that I want to briefly touch upon as that today's lecture goes. So I will start with this, how I can connect this with the AC transport in kind of following way. So let's start with a very simple model, so-called the Lorentz oscillator model, which is kind of very simple, right? So I have this mass that attached with a spring, and that this mass has a charge E, and that, so I will just kind of think about this as electron that bound into something, can be bound into each other or molecules or impurities, doesn't matter. It's bound. It's kind of bound with some well-known spring constant, so it will be oscillating with some natural frequencies. I'm just applying the AC electric field, and then just kind of course the oscillator will be oscillating, and because the charged object is oscillating, I can define the current, and I have the electric field, and I can define the current, and you can ask that. What is the conductivity of this system? This Lorentz oscillator model has been kind of solved multiple times, and you can quickly see that if you calculate simplified form, something like this, right? And I can plot it out that how the conductivity of this system got changes as a function of the frequencies, right? And of course, there is the resonance frequency. There, the conductivity is kind of the diverge upward, the downward, right? Something like this can be seen. By the way, sorry that this conductivity is divided by I. So this is not the real imaginary part of the conductivity. I just made a typo here. So that's kind of important part, right? Otherwise, negative real part of conductivity is problematic, right? So this is imaginary part. But the important part is that across omega c, the sign of the imaginary part got changes, right? Conductivity. So let me see that, right? Something else I can do this right. I think that I can say that in terms of impedance, I can have the resistance is same unit as impedance, and the inductance comes with in this way, and capacitance comes as impedance in something like this, right? So since that sigma is 1 over r, so you can see that inductive component is something like this, and capacitive component something like this, right? So what I'm saying here is if I just look at the real part, the imaginary part of the sigma, I can immediately read it up to whether this is more inductive versus capacitive in this part, right? So you can see that in the frequency lower than omega c, that conductivity, imaginary part of the conductivity can be viewed as the capacitive couple, right? And frequency larger than omega c, whatever the characteristic, this one is always kind of inductive, right? So I can see that by just measuring the AC conductivity, depends on the frequency ranges, compare with the characteristic, the frequency. I can just read it up that this could be kind of more capacitive and inductive, and that already gives you some of the information, right? So my talk, they were two parts, and one is first part is inductive, and second part is the capacitive. So inductive part is simply that making omega c goes to 0. In other words, basically there is no binding, right? So free electron, but then free electron over the finite resistivity, which actually is not captured in this model. So I want to clear that resistivity, which means that I'm dealing with a superconductor. So the first part is basically that I have the superconductor, just measuring the AC conductivity, which is basically kind of purely inductive. And from there, I can get the information. And what information you can get from this Lorentz model already get more like you will get this some charge carrier number density n divided by the mass. And the very important quantity that related with this superfluid stiffness I'm going to introduce in a moment. That's kind of something that I'm going to measure. And second part that if time allows, I will just kind of go for the other limits, the capacitive part. And here that I need kind of some sort of some finite binding energies, which is much higher. And example I'm going to use is basically quantum Hall system, especially if you just kind of measure the bulk of the quantum Hall is an insulator, right? And binding energy is kind of related with the, in this case, the cyclotron, the frequency, which is kind of quite high in the regional frequencies. And that's kind of where I want to kind of see that what type of the capacitive or the dielectric response I get onto the topological insulating states, right? The quantum Hall insulator, the bulk of the quantum Hall system is basically an insulator, right? So I ask that what type of this the dielectric response I get onto that, and that's also something. And you can see that that is related with again the potential quantum geometry, as Ken mentioned. So let's start with the first part, superfluid stiffness, and I'm going to show you the experiments. And that this experiment was done by the many collaborators, but the main person who did the experiment here is Abhishek Banerjee in collaboration with the JU and the Mary. I think these three people that plays a very important role through there with the theory support from the Ashwins and then the collaborators. Okay. So we know that superconductor has a kind of two important properties. Anyone that claimed the superconductivity U1 has to demonstrate I have the zero rigidity at some below the critical temperature and Meissner effect, and that's kind of two important part. While these are kind of two rather separate phenomena, there's a kind of really nice way they tucked in that these two properties in one equations, especially if you just choose a gauge right. Simply just write down the London equations with the London gauge in terms of the vector potentials. You can explain that both the perfect conductions and perfect diamagnetisms in there, right? And if you just look at this London equations, basically that's related with the supercurrents, with these vector potentials, with this parameter. And this parameter is a kind of naturally consists of the superfluid or super the Cooper pair density. I would say that as this superfluid density. Doesn't matter, and then divided by mass, and on this quantity. So n over m is naturally comes around in here again. And what you see here is basically this is kind of important governing quantity. And often this is kind of what people call the superfluid stiffness with the coefficient kind of h bar square over 4 in front of it, right? And in some sense, the superfluid stiffness, therefore, is a quantity that most two physical properties appear in the superconductor. And the name of the superfluid stiffness comes in fact, coming from that once you just write down Ginzburg-Landau energies of these superconductors, and then those the same quantity appears in terms of this the parameter governing of this superfluid the phase stiffness, and that therefore that the superfluid stiffness actually often comes from that the names from there. That Ginzburg-Landau the energy rational. Okay, how to measure this superfluid stiffness? Okay, what you are seeing here is that because this superfluid stiffness is governing both of the magnetic properties into the system, especially kind of shielding properties. So it's clear that once you just kind of look at the magnetic response, you can get this information about superfluid stiffness, especially if you just write down the way, what is the magnetic the penetration length, or the lambda, and the lambda is purely consists of the superfluid stiffness in there. So in a sense, if I just measure the penetration length scale of the superconductor, that will immediately estimate the superfluid stiffness. So there are ways that one can measure the penetration length scale, and way that you can just do that is they put the sample in some the microwave cavity. And just look at the volume of these penetrations out of the response, you can get those kind of informations. Especially sample is thin film or the small, and often that a little bit more the developed technique is needed. One of the technique is a so-called this mutual inductance measurement to work well with the films. So if you have the film, you just have the two coils in both sides, and one coil excites the magnetic field, and the other one kind of try to detect any magnetic field penetrating through this the film, and that will contain the information about again the penetration length scale, and that's kind of typical way that one can use to measure the superfluid stiffnesses in there. And of course, this is kind of some method has been used widely to many different systems. Including the conventional as well as the unconventional superconductor, and the very important information to argue about the property of the superconductor. The superconductor I'm going to deal with today is the twisted graphene device, the magic angle twisted bilayer graphene, where that superconductivity appears potentially is coming from some sort of correlation effect. And the phase diagram is kind of rather interesting. In fact, if you just look at the phase diagram of this twisted pin, initially the people see that there is a bit of the analogies of the phase diagram of the superconductor at high temperature superconductor, roughly saying that you have this the magnetic insulator, the antiferromagnetic insulators, and that doped antiferromagnetic insulator, you get the superconductors in this kind of dome shape of the superconductivity appears, and a lot of the broken symmetry states kind of the competing or that coexisting with this the superconductivity, and very similar way that in the analogical way that if you just look at the phase diagram of the twisted bilayer graphene, superconductor appears onto the initially was mouth insulator, then assigned, but later that we know this is not mouth insulator, rather it is more different type of correlated insulator, which often has a Chern number. And anyway, that some broken symmetry insulators that when you just dope it, then you get this kind of superconductivities up. Often that superconductivity is near by that this correlated insulator, and there may be some interesting analogies there, right? And it has been argued that, or it has been kind of multiply shown that indeed here that the superconductivity appears in the cuprate is non-conventional. So the one argument, one thing, interesting argument we want to kind of make is whether the superconductivity appears is twisted bilayer is in the analogical way that is unconventional. So one thing that we know that in the twisted bilayer graphene, in terms of this electronic property, is that has a kind of different way of breaking the symmetries into the system. And as a graphene system, there's usually spin degree of freedom, and there's valley degree of freedom. So often just degenerated in the very single particle point of view, often just give you the SU4 type of the phase space to kind of deal with. But once you have this flat band forms in the magic angle twisted bilayer, and this strong correlation coming from the flat band, they actually break this the symmetry or degeneracy in the system, and this kind of broken symmetry appears. And then in terms of the many different type of measurement, people have seen that the symmetry is kind of broken, and either first order or the second order, and often that this broken symmetry states give you that a correlated insulator, where often that the certain correlated insulator has some generalized magnetic order, that in other words, the SU4, the spinors kind of pointing in some particular direction, can just describe it as a generalized magnetic order. So again, that analogy kind of works quite kind of well among each other, right? So there's a way that we want kind of look at this one a little bit more quantitative way. So that's kind of something that that comes around. Now, twisted bilayer graphene, by the way, has a lot of the real experimental issues. Part of the reason is that because you can imagine that this is kind of two single atomic layers, just put them together, there's always some residual disorders. It's a very difficult to control, right? You can think about somebody giving two sarin wrap and just can put them together with kind of exact kind of certain twisting angle between them. You can just do that, but you can imagine that there are a lot of wrinkles, and that the wrinkles and then things and this kind of, you can imagine all sorts of things, right? So experimentalists need to deal with all these things. One of the ways that we can get around that is getting a little bit thicker sample, or that more of the layer. And indeed, when the theory first comes around, instead of twisted bilayer, if you go to the twisted layer, 3-layer, 4-layer, the very similar physics can be translated into this multi-layer, in a sense that twisted bilayer, that if you just control the angle right, that you get this flat band appears into the twisted bilayer. But if you go to the twisted multi-layer with kind of well-controlled angle, although angle can be different, but if you just kind of tweak this angle the right, you can still get the very flat band, even for 3-layer, 4-layer, right? And then there's a kind of another dispersive bands around. Usually this dispersive band does not interact with the flat band strongly. So you can more or less get this flat band physics out of multi-layer. Though this multi-layer is more layers available, they are a little bit more rigid, and there's kind of the self-locking mechanism, the bit more robust the system. So experimentalists, in fact, make the multi-layer, 3-layer, 4-layer, unlike the single layer, among various different experimentalist group, at least their consensus can be made. So that's kind of interesting part. But nevertheless, yes, please. Yeah.
These figures you showed are for the same twist angle between the first and second, and second and third, right?
Yes. So So you have to kind of put the first the kind of angle.
Beyond bilayer, you have the problem that in experiment it will never. So
that's right. Yeah.
It seems
So you need a little bit of the compromise in that way, right? If you have really good experimental, you're not experimental, so are you? No, all right? They're really good experimenters. So I can make this kind of the angle mismatch between the layer, let's say 0.1 degrees, right? And then probably 4 or 5 layer, I can just do that, right? But then eventually, if you just put too many of them, even 0.1 degrees, that it give you the quite differences, right? So depends.
0.1, like what's the super more?
Yes, again, okay, going to the detail, then if the angle mismatch is a lot there, then there's supermodel comes in, and maybe super physics gets in there. It becomes kind of complicated matter in the end of the day, but usually 3 or 4 layers, the various different groups, their result is very similar to each other, right? Yes, there are supermodel effect, but those this high order effect is often much weaker.
So you don't experiment.
We do see that if you look at the detail. Physics I'm going to discuss is probably not focused on that part, so it's okay. Yeah, good point. Right. So I will skip few things here, but then just discuss. Now, since I just introduced the multigraph layers, I'm going to discuss about 3-layer system for now. But nevertheless, claim that I'm going to make here is conductivity we are seeing here might be unusual, unconventional. The first thing that I already mentioned, that the superconductivity usually appears very close to the certain correlate state. The experiment I just skip it over is basically, especially the particular superconducting, the broken symmetry state, so-called the nu equal 2 to the 3, is important. The ranges that the superconductivity strongly appears. In other words, among these many different type of magnetisms possible, the certain magnetic ground state is that strongly harbor the superconductivities once you adopt those of strongly correlated systems. So, which actually is one the evidence. The other one is that there are a few other things, and that critical current nemestics, in other words, that there is a directional dependence, and that there are some of the other broken symmetry state appears. In plane magnetic field, especially applied, superconductivity survive up to many Tesla, strongly break these Pauli limits. That, in other words, again indicating that maybe the Cooper pair is made of the equal spin potentially. And then spectroscopic result coming from the STM also give you that gap is not cannot be easily explained the BSS type of the things. All these things is one part. But the other experiments that shows that a few years ago is measuring superfluid stiffness. They start to see that the superfluid stiffness is much larger than what is expected from simple band type of pictures. I'm going to explain that in the later a bit more, and has some characteristic behavior that out of this superfluid stiffness, which cannot be easily explained in terms of the conventional view. Okay, so that's the part that argued. Right, so let me just break down this argument a little bit, and let's go through that. When we say the unconventional superconductivity, there are many different ways that we can claim the unconventional superconductivity. Probably Andre is going to discuss more about these things. But one way just is look at this, the superfluid, the order parameter symmetry. BCS, and the phonon-based BCS, we expect to see that just S-wave type of order parameter symmetry. Cuprate, in many ways that we know that it is a D-wave symmetries, right? But then if it is logical in the 2D, there might be the P-wave type of symmetry. There are various way of the different type of the order parameter symmetry exists. One thing important part is that away from this S-wave, the order parameter, there is always nodal point into the superfluid, this superconducting order parameter, which means that at the finite temperature, the superconducting gap closes down somewhere in your momentum space. What does it mean is basically as you go to the finite temperature, you can always excite some of the quasi-particle states. Now, since the carrier is fixed, and they are condensed in the 0 temperature into the all Cooper pairs. But now that at the finite temperature, there's all quartz particle can get excited. So this means that if somehow if you measure superfluid stiffness, in other words, basically superfluid density by the mass, superfluid stiffness will decrease as you increase the temperature, right? And indeed, that's kind of the one of the experiment has been done in high temperature superconductor, right? I briefly showed you that people just put the YBCO crystal into the microwave cavity and measure the penetration length. And inverse of penetration length square is basically proportional to the superfluid stiffness as a function of temperature. What they see that is those kind of the penetration length is actually decreases linearly, fairly strongly in the low temperature region, right? And that's basically indication that indeed there is another point into this superfluid stiffness, right? So that's one part. Potentially, we just do the very similar experiments onto this twisted bilayer graphene and then see whether we can just see those kind of effects in there. The other thing that the unconventionalness is basically comparing the gap with the Fermi energies. And the typical superconductor, of course, in the conventional superconductor, gap is much, much smaller than Fermi energies. Turns out that if you just do the very similar analysis into the many unconventional superconductors, including the cuprate, this ratio becomes kind of much, much larger than unconventional superconductor, where that the ratio is kind of really small. And often that this plot, including that the twisted bilayer graphene, is kind of often people call the Uemura plot. And the reason it's called the Uemura plot is the Tomo Uemura, who actually first showed that indeed the cuprate, if you make this ratio, that is kind of really higher than the conventional superconductor. And this higher numbers, higher ratio means that somehow the Cooper pair is really binding strong and showing that kind of unconventionalness in there. By the way, how to measure this TF or the Fermi energies is a kind of an issue. In fact, if you just kind of manipulate the EF in the parabolic system, EF is related again the superfluid stiffness at the 0 temperature limits. And that's kind of the experimental way that you can plot it out. Indeed, the proper way of plotting this Uemura plot is measuring the TC of the system and measuring the superfluid stiffness and the 0 temperature limit, and just show that where that it lies onto the Uemura plot becomes kind of important, right? Okay, so that's the part. Okay, so this gives enough more. Yes, yeah. Decrease with the temperature. Yeah, because simply that I would say that, well, I can come back in later, but let's see. It's a proportional to N of M. Right. Right. So this is decreasing and this zero decrease. Right. Okay. So the problem of we have the measuring the superfluid stiffness is all of the conventional way that we can just try to measure superfluid stiffness may not work too well. And part of the reason is most of the twisted bilayer graphene and that we are dealing with is a very small size, about a few microns at the most, right? And the conventional way that putting into the microwave cavity or the sample volume is small, right? To try to basically your pickup coil need to be much, much smaller than then kind of developing this one. It's basically engineering challenges, right? However, there's kind of clever way that one can measure the superfluid stiffness out of here. That's basically, we are just looking at the magnetic response of the system, right? That's kind of where that we can use so-called kinetic inductance measurement. So what is kinetic inductance? Let's say that I have the sample, thickness of D, the width of the omega, and the length of L, and I just write down what is the current, the flow in the system, but simply just kind of write down current will proportional to the number of the carrier here, times of the velocity of the carrier, and then all the other geometrical factors are multiplied, right? Now, I just write down the current in that way. We can just ask a following question. Now, current is carried by this carrier, and since carrier is moving, you can ask that what is the kinetic energy of this carrier altogether, right? So if I just ask what is kinetic energy, it's half of the mv squared. That's simple, right? But then I have to know that what is the number of the carriers there, and total number of the carrier I have to multiply the volume, right? So I can write down this is the total kinetic energy of the carrier carrying the current in my sample, right? So let me rewrite this kinetic energy in terms of the current, right? Because current is proportional to this velocity. I can just rewrite this one. And obviously, this kinetic energy will be proportional to the current squared. And then all other numbers are tucked in there. That is basically, rewrite that number is basically this one. But look at this, the relation. In the end of the day, I have energy in this side, and the other side is the current square, and there is coefficient in front of it, right? If you just go back to the basic, the general physics in the freshman, basic inductor, there's a carried current, right? Ask that what is the energy stored in inductor. Basically, this is exactly the relation, right? So in some sense, that what this tells you is basically I can just look at the kinetic energy of the carrier is basically behave like the inductor in the system. And that's precisely that discussion I had in the Lorentz oscillator model, right? When I just look at this Lorentz oscillator at the any finite frequencies, there's an inductive response, and that inductive response is precisely kind of this form, right? So that's the way. Now, note that this can work with any conductor. Doesn't matter, right? I can always kind of doing that. But we rarely just discuss about kinetic inductance simply because this kinetic inductance compared with the geometrical inductance coming from this the sample, where that real magnetic field is created by the current, is very, very small. So it's completely ignorable in typical conductor. Except that if I just kind of try to make that this kinetic inductance becomes large, the way that you can just do that is if I make that this thickness is smaller and smaller, the compare with this the geometrical inductance, once you bring to the system the 2D limit, you can show that indeed kinetic inductance start kind of dominating over the geometrical inductance. So once you get into this low-dimensional system, especially two-dimensional system, kinetic inductance becomes really appreciable into the system. Indeed, this is not just a kind of written simple theory. This is now almost commercial product out there. People just did make this superconducting thin film, and just measure, they make this kind of the lines, and then measure the AC response. And then this AC response will just the kinetic response out of that. And based on the AC, you can just kinetic inductance comes out. And any particle comes in from the out there and break the Cooper pairs and reduce this the inductance changes, kit got changed. And using this one, people just can make the really sensitive detector. And often this type of kinetic inductance detector is what astrophysicists do, that proving the outer space probing there. In fact, actually, heard about the kinetic inductance, my astrophysics colleague asking that, oh, yeah, we are using kinetic inductance that the detector. I was asking, what is kinetic inductance? He was asking, I thought your computer physicists know about this. So kind of, but anyway.
Model.
Yes, if I set the Lorentz model that omega c goes to 0, basically the kinetic inductance is naturally comes around, right? But simply in bulk system, this is the really ignorable compared with the geometrical inductance. So usually we don't consider this at all, right?
It's
But
just kinetic energy.
yeah. Kind of, yeah. All right. So kinetic inductance is therefore that's something that we are using to measure it. The relation between kinetic inductance and the superfluid stiffness is actually inverse, as you see here. So that's kind of the relation. If you just look at the kinetic, the superfluid stiffness, usual relation, you can write down in terms of energies, which actually divide by the Boltzmann constant. I can just use as a Kelvin as a unit. And you always say that is useful to the quantity, I can just use it. Or the more of the engineering side, I want sometimes it kind of quote that inverse of Henry, that explicitly showing the kinetic inductance. So experimentally, what we are going to do is we'll just measure kinetic inductance as a function of the temperature of the system, right? And the idea here is if that the kinetic inductance, the inverse of kinetic inductance, which will give the superfluid stiffness, is decreasing with the temperature rather steeply and especially linearly, and that's more like the kind of pointing out this is nodal superconductor. If it is more like the nodaless superconductor, S-wave type of things, and you need kind of the quite higher temperature, start exciting this the quasi-particle beyond the superconducting gap, and this kind of the exponentially activating behaviors appears really kind of slowly with a finite gap. So whether there's a slope or not, or at least say that what is a nodal superconductor or not, and particularly that this slope and that kind of careful analysis even get the information about whether what is the quasi-particle dispersion and what is the nodal velocity, and those kind of things can be done, right? So that's kind of experiment we want to do. Now, actual experiments is actually still not too easy. The part of the reason is that, or that's why that AC transport is not easy things you can do. Especially that the measurement we need to do here is something that range of several hundred megahertz, even just gigahertz ranges. Part of the reason there is that you want to kind of avoid that kind of various things. That basically you have the kinetic inductance we are measuring, sample size is small, so it's a very small inductance we are measuring, right? And that to get this enough, I have to kind of go to the higher omega, right, to get this kind of the compensated small L. And all these things basically give us a really tight kind of stringent kind of relay, the condition that I have to do the experiment with something like the hundreds of the megahertz at least, right? And then our sample is sitting inside of the fridges. I have to deliver this the microwave down to below there and coming out. So that requires quite of this circuitries there. And more difficult part is that typically this microwave and the RF measurement is always kind of matched with so-called the 50 ohm of the resistance. Many theorists cannot see that. Why is just to do that? Why 50 ohm, right? First of all, experimental instrumentation that you need to buy this one for the microwave, it's always 50 ohm matched, and that's a standard. And there's a reason for that, because I think the vacuum impedance is about 300 ohm, right? And all of these things, microwave, the circuitries are developed with the radio type of these technologies. So 50 ohm is kind of really natural that you can match it. So what is the problem is most of the resistance on the impedance level is something like the kilo ohms, tens of kilo ohm, right? So to deliver the correct amount of microwave powers in there, you have to go through the microwave circuitry, so-called the matching circuits, such that I can deliver the power right to this long distance to the sample, and also getting the powers out. So all that is kind of technical difficulties. You don't have to appreciate it, but it's harder experience than DC measurement, right? But in the end of the day, just this is basically what data look like. So here's my sample, that this is a twisted tri-layer, becomes a superconductor at the certain gate voltages. So this is at the sample that I'm changing gate voltages. I convert this gate voltage conveniently, what is the Moire filling. And then what you see here is around the nu equal 2 electron field Moire, and around that area that becomes a superconductor. As you see, the resistance goes to 0, right? So that's basically we have the superconductor, more like the hole like the superconductor, electron like the superconductors in this sample. So that is a DC transport measurement we discussed, right? Now in this sample that we just convert our circuits such that this is my device sitting it there. Now instead of I'm just doing the DC, I just send this microwave from the outside of the fridges, get in there, and throughout this matching circuit, I deliver the right amount of power into my device. Now note that especially when my sample is a superconducting states, that there is no resistance anymore, that all this thing is inductive, So I can just kind of put out this inductive load. However, all these devices connected with all this conventional the electrode, including that finite contact resistance. So I have some resistive part in there. But nevertheless, this is basically the RF circuitry there where the RF comes, the microwave comes in and the reflected back, right? So I'm just looking at the sending the microwave in and microwave comes out and just kind of look at the response of this one. So in other words, changing the frequency of the RF circuits, the radio frequency I'm just putting there and reflected back, what is the amplitude of this reflected microwave and what is the phase difference between the reflected microwave between that injected microwave. So that is experiment. And that is what we often call this microwave reflectometry, right? In fact, this is what people just are doing with the qubits. You make the qubits, send the microwave, and just kind of get this microwave back. And just looking at this reflected microwave, you can get the cubic states as well. So this is kind of similar experiment in that way. Right. So this is basically a microwave reflectance signal, as I'm just going to show you. So this is a reflectance. So you can have this reflectance coefficient. So that has a magnitude as well as a phase. I'm showing the magnitude only here. This deep blue color is where that there's a deep appears in the reflectance in the frequency ranges. And I'm just tuning the gate voltage. So if I just make this cut, you can see that there's a dip appears, so some sort of resonance appears, right? And as you change the gate voltage, those kind of resonance kind of changes. It's a width as a position got changes. At the same time, if you just look at the matching signal for the phase, also phase got shifted, the phase got changes, things, right? So that the magnitude, frequency, and phase got shifted because everything got fixed except that by changing the gate voltages, the inductance got changes, right? So careful analysis of those kind of shift of the frequencies and the width and those kind of information will give you this information about the kinetic inductance in the system. You can always see that whenever that we get into superconductor, there is a frequency shift that appears. And the frequency shift is indeed directly related with the kinetic inductance shift. So you can already see that there's effects in there. Now, the next slide, I'm going to just kind of skip it. What you can do that is you just do the gate dependence and temperature dependence, measure all this reflectance signal, and then you carefully analyze the ways of frequency shift, what is the amplitude changes, what is the phase changes. In the end of the day, extract what is corresponding this kinetic inductance out of system as a function of gate voltage as well as temperature. So that's basically experimental outcome that we have. Yes? Yeah.
Previous slide, you kind of drew where superconducting regions were.
Yeah.
It's nice to that
Yeah.
the shifts of the frequency.
Yeah.
But there was like one part of the data where it was outside of the superconducting where that you drew and it had
Something like this?
yes,
Right.
yes.
Yeah, so what happened here is that this is where that so-called correlated insulator has, right? So there's your sample is not an inductor anymore, right? It becomes kind of really resistor with highly resistive resistors, right? So if you just look back this one, right? Basically, okay, here, this resistance, right? So what you see here is that not only inductance change of the resistance changes, will just change around this response, right? Basically, this is the complicate the network of the RLC. I'm sending the microwave in there and comes around. Either kinetic inductance changes or the resistance changes, all kind of changing this the response of the microwave, right? So that's not surprising that it's not only changing within the superconducting regime, the outside as well, right? Good. Right. So once you get this, now we can just do the following things. So since the kinetic inductance inverse of the kinetic, yes, yeah, yeah. In principle, it can be anisotropic, right? We cannot do that at this point. I will just hit that point in a moment. Hopefully, what time I have to stop? Oh, gee, okay. Maybe I have go for the my third lecture start kind of contain this one, but okay. So let me not speed up because I think that's not the point of this the score, right? But yes, that's a good point. I think that especially if it is nodal superconductor, in principle, that there is some directional dependence in there now, right? Okay. So I'm just kind of plotting the kinetic inductance, inverse of the kinetic inductance, which is basically the now superfluid stiffness, right? So this is as a function of temperature. I cut it out at several different gate voltages, right? So just looking at this, already you start to see that interesting observation, right? First thing that you observe is kinetic inductance drop down rather sharply as a function of temperature at the low temperature region, right? So just looking at this one, I know that this must be nodal superconductor, right? Because that's kind of what we are seeing. And second interesting part is, if you remember that the zero temperature limit of the superfluid stiffness is also important because that is related with the kind of the T over the df, or the T over the quantity that related with how strongly coupled the superconductor it is. So one can just kind of try to extract this zero temperature limits of the superfluid stiffness, and then let me just kind of plot out that the zero temperature limit of the superfluid stiffness as a function of the filling fraction or the gate voltages that we changes, right? What you are seeing here is that there's a nice dome shape of the zero temperature limits of the superfluid stiffness comes around. In fact, this dome shape of this superfluid stiffness zero temperature limit is pretty much well correlated with the transition temperatures of the superfluid, the superconductor we measure in terms of the DC transport. As a function of that, if I just rescale this axis, they actually overlapped quite nicely, right? So the first thing you start to see that is that this zero temperature limit of the superfluid stiffness is well correlated with the TC that we are measuring across this dome, right? So the other part is what about this slope, right? There's another information that from the slope, and this slope is also changing with the gate voltages. So I can just kind of take the slope and plot it out as a function of this filling fraction. Slope also shows kind of intriguing behavior, right? There's a steep slopes appears up to here, but suddenly changes. So if I call this is optimally doped ranges, across these optimally doped ranges, that there's a kind of rather strong changes of the slope. So can I just explain this? Basically, that's the part. How can I just explain this type of behavior where we are seeing, right? This two behavior. Explaining this two behavior is something that we can see. And there, basically, I can use this superfluid stiffness and explain this part, right? So let's say that indeed the zero temperature limit is something related to this, right? I want to explain that somehow this, I'm just changing that the filling. But how we can? Well, in fact, this is what already has been done for the D-wave superconductor Q-plate a long time ago, right? If you just think about the nodal superconductor, and nodal superconductor means that the quasi-particle has this dispersion at the nodal superconductivity in this way, right? So if I call this is quasi-particle dispersions in this way, right? I can just kind of think about just I'm filling up this the quasi-particle dispersions. As I was filling up this quasi-particle dispersion, at some point, basically you can see that electron like the quasi-particle that turn into hole like the quasi-particle, and that will just kind of say that your mass got change sign in there, right? So generalizing this into the this type is that the nodal dispersion is a real this one, NK is basically filling up this one, where that the mass is a second derivative of basically of M analyzed for this nodal the superconductor, and that sharpened when many years ago, right? And then you can even just write down second term. What if now you go to the finite temperature? Finite temperature means that this dispersion relation, quasi-particle dispersion relation, start kind of the thermally excited, that two carriers, the electron like the hole like the quasi-particle carriers, right? And you can easily write down those kind of the excitation, just knowing that what is this nodal gap structures, simply write down in this way, right? So what is, if I just borrow this expression from the cuprate, I can immediately see that how this rho of S with the temperature is changing here. And simply that this new changes is I'm just kind of changing across this nodal superconductors, right? And with this, I can explain basically how that the slope that I'm seeing changes at the zero temperature limit. At the zero temperature limit, basically this part is go away, and simply looking at this one, right? If I know that what is the dispersion relation of this quasi-particle, and I should be able to just compute what is the loss of S should look like. And dispersion relation of this the quasi-particle, if I just look at this by theoretically, they provide the Hartree-Fock band structures between the nu equal 2 to the nu equal 3. There's strong electron and hole, electron-like the band and hole-like the band asymmetry is there. And just kind of following through this one, I expect to see that at the middle of this one, I get the electron to the hole changes, where that basically mass or derivative got the sign changes. So if I just filling up the band, initially I just filling up the band, but then mass term, that second derivative got change the sign, then I start kind of filling up this one, I start to decrease, and that more or less explain that qualitatively this thing. Also, this nodal velocity is nothing but this slope. You can see that this also changes that this is steeper and this is slower, and that can be actually mapped into the more or less this type of behavior. Again, one can do this one a bit more quantitatively, just with this one. So what I'm saying here is at least that if I just assume that the particular shapes of this dispersion, that we can see that measure this the superfluid stiffness can be explained at least in the qualitatively with using this simplistic the quasi-particle dispersions I can just have. I think that I just kind of run over the time. So rather than I just the speed up, let me stop here. And my third lecture, I will kind of pick up from here and also discuss a little bit of the other part I just prepared. Thank you very much.
If you plot the other parameters on top of this plot of rho and
yeah,
critical, roughly how does it look like? Does the other parameter at zero temperature?
They more or less overlap. I think that's kind of the discussion I need to go.
Same shape?
Same, very similar shape. And that there is parameters that get involved there, which I need to discuss a little bit more. Yeah.
But if you plot all the
yeah.
Scale by a factor?
Yes, there's a scale by the factor. So something like this. Yeah. Let me just grab this one that discuss the next time because I need a little bit more discussion for that part. Yeah. But going ahead. Yeah.
Very last slide.
Yeah.
Given that much.
Yeah. Yeah.
The image negative. That means it's negative.
Basically, it's accumulate from the bottom, right? So yes, indeed, it cannot be, but it was basically. I'm saying that it was a non-monotonically behaved. That's kind of what is going to be clear.
For conventional case, it's the right formula. If you EF over 4 pi, the K square over 10.
If I have the parabolic band, yes, yes, right, yes. Well, that's basically happened that, or it's actually increasing, but then start to decreasing. right? So that's yeah. It's not me that wrote down this one, by the way, right? You have to argue with these guys, but yeah, yeah. Well, the one way I can argue that is indeed actually later on that I can show you that with this the plugin that kind of write dispersions, simply just kind of compute this one, right? And just kind of compare with this one. Let me just kind of go ahead because you're saying the formula is correct, but my interpretation is wrong. But then I can show you that later. Yeah. Where is it? Okay. I think this, for example, this, right? This is basically kind of according to the dispersion I just computed out, and you get kind of more or less, I mean, it's not exactly match, but then actually followed at least qualitatively, that kind of what it look like. So formula is correct and interpretation might be correct. So in that regard, yeah.
This kind of formula assume that air potential is only depends on moment of breath, right? And so that's unlikely to be true, at least when the filling factor applies. So in that connection, I have a related thing.
Yeah.
Most recent experiments of the best samples we could make.
Yeah.
Would you say consistently you see superconductivity between filling factors 2 and 3?
Yes. Yeah. I think.
So, what was going on with early samples? Just
note that the earlier sample is mostly in the twisted bilayer, right? So. Yeah, so the many of all of this experiment now is a twisted multi. That more of between is very small. Yeah.
Something related. These kind of samples are really like man-made sample, right? Hidden sample.
Yeah.
What's the typical yield of this tri-layer, multi-layer samples that actually exhibiting superconductivity, and how long does it take to that kind of process? Just like we have a lot of theorists here, they should appreciate asking friend aggressive and spend time in
I would say that that's a rather difficult to just quantify. I think the good students can produce this type of the sample better, right? But 1 week at few sample is a very kind. But let me put it this way. I think that what is it that the Pablo published this paper in 2018, so it's now 7 years. Now it's twisted bilayer, tri-layer, 4-layer, 5-layer. I think probably up to the 6th-layer the demonstration. How many samples in the world we have showing the superconductivity? Let's put it this way, right? Well above tens. It's probably about hundreds sample, but not high hundreds, right? So there are groups, many students work on there, but I think the best quality sample also is a little bit difficult to come by. I think probably if I just go ahead, show you one slide. Something like this. I think these are the collection of the sum of the samples that we measure superfluid stiffness and just try to compare with what is the effect of the disorder and things. How many samples? I think probably about 5 or 6 of those kind of samples. And this measurement that we need a lot of the statistics, so we just use the best sample that the samples available in the group, and that's not enough. So we actually asked Pablo to provide some samples they made and just measure these things. And what you're seeing here is about kind of the 10 sample-ish, right? This is more like the probably about 50% sample that we produced so far, right? So that's kind of provide the numbers there, right? So it's not a sample to combine. There are a lot of samples, so probably worldwide is right. For the twisted multi-layer sample in the right condition, they have the reasonable consensus, I would say, right? So that's that much I can say.
So by 2 to 3, do you mean -2 to -3, or do you mean superconducting dome, the additional on the particle side?
So both 2 and 3, 2 and -2, often that is it's very strongly on the 2 to 3, right? But often that the below the 2 also sometimes, right? So 2 to 3 is all the times. Same as a -2 and -3, by the way, right? And sometimes superconductivity dome appears slightly above 2 or slightly less than 2, right?
Measurements, are -2 to -3 basically the same as 2 to 3?
Not different. Depends on the magnitudes are sometimes stronger in the positive, sometimes stronger in the negative. But yeah, that depends. I don't think that I can make the general statement for that. Yeah. Yeah.
Just if you're not in the field, is there a strong reason to understand this particle hole asymmetry?
Yes, the band itself is a very particle or asymmetry. That's kind of first part, right? And when you just go for therefore the broken symmetry states also, that's there's no reason to believe the symmetry. Yeah.
Question? Then let's.
All right. Thank you. Yeah.